All right, so yeah, we have the last speaker for today. It's Javadekar, and he's going to talk about triangulated categories.
Okay, thank you for the introduction. So I'll be talking on triangulated categories. So the goal is simple. I will define what a triangulated category is, and we will see one or two examples. So there are many experts here, so please correct if I do anything wrong. And I hope there are a few graduate students for whom this may be a new concept. And this has come up in, I think, almost all the talks before that. Some categories triangulated, so at least we will try to see definition and an example. So I hope everybody knows what a category is. So it consists of objects and you have morphisms between them. For example, category of sets in which morphisms are set maps. We have rings in which morphisms are ring maps. Category of modules over a ring in which morphisms are module homomorphisms. In topological spaces, we have continuous maps as morphisms. So that's a category. So I will be mostly working with algebraic examples. So yeah, so that's category. And for example, if you consider category of modules, we know that there are some special objects, like we have zero module and we have zero maps. So a category which satisfies, also in category of modules, we have direct sums, direct products. So we make this notion abstract, and a category which satisfies some of these properties, we give it a name and we call it as an additive category. So what is an additive category? It has to satisfy three axioms. So first axiom is that, so yeah, I'll be denoting category by letter C, and morphisms between two objects, X and Y of C, will denote it by OMXY. So what is an additive category? It has to satisfy three axioms. First axiom is that if I take two objects of category C, then the morphism set, this should be an abelian group. So I would suggest that you can think always at the back of your mind that we are working over category of modules over some ring, commutative ring with unity. So OM should be an abelian group. Then second axiom is that there should exist a special object called zero object, such that OMs from zero to any other object, this should be the zero group, and OMs into the zero object should be the zero group. And the third property is that suppose you consider two objects in category C, then so for any two objects, there should exist an object Y such that we have this. So from X1 to Y, there is a map. This is identity. So it's like we have a map I from I1 from X1 to Y, I2 from X2 to Y, and let's call these as pi1, pi2, such that I'll just write. So I1 followed by pi1 is identity on x1. So think of this x1 as a, think of this y as x1 direct sum x2, so that this map is an inclusion and this is projection onto x1 coordinate. And more or less we are trying to formalize it here. So, and then same for I2 composed with I2 is identity on x2 and I2 composed I1 is 0, I1 composed I2 is 0, and I1 pi 1 plus I2 pi 2 is identity on y. So if the category satisfies these three actions, then we'll say that such a category is an abelian category.
So also need a composition to be composition to be by
Yeah, right. So yeah, I also need that compositions are bi-additive or bilinear. That means it's like composition should distribute over addition. Yeah, so this is what an additive category is. But now if you think of category of modules, we have some more structure. Like we have objects like kernels and co-kernels. So what is a, so suppose you have a morphism from x to y, then kernel of this map is an object k together with a map such that whenever you have any other object with the property that from k to x there is a map satisfying psi followed by phi is the zero map. So suppose that we are in an additive category, so that zero maps and zero objects, they make sense. So if this composition is identity, then there should exist a lift from k prime to k, making this diagram commutative. So this k together with an I, we call this as kernel of this morphism. And dually we have notion of co-kernel, in which you have a map from x to y, then maybe C is said to be co-kernel C, pi if for every map from y to some object z, such that if this composition is 0, then there should exist a lift from the co-kernel, making this diagram commutative. And we know that for category of modules, this if we consider this to be a module map, then kernel is the usual kernel, the set of all elements of X which send which are sent by phi to 0 here. So yeah, so this K turns out to be a subset of this X in that category of modules, whereas here for a map from phi from X to Y, the co-kernel is Y modulo the image. Yeah. Yeah, so what is an abelian category? So something that has this structure in it. So an abelian category is an additive category. Plus one more axiom A4. And what is this A4? So given any phi, a morphism from X to Y, it should have kernel, it should have co-kernel, and it should satisfy something more. So this is the map phi. So kernel should exist, co-kernel should exist, and this object here should be kernel of this map, at the same time co-kernel of this map. And in case of modules, this is just isomorphism theorem. That is, if we have a map from X to Y, then this I is X modulo the kernel, which is isomorphic to the image. Okay, so this is what is an abelian category. Just add it here. Then once we have an abelian category, we can talk about complexes in that category, because we have access to kernels and co-kernels. So suppose A is an abelian category, then we can construct or consider complexes in this category. And this is the convention that I will follow, that the index goes on decreasing, and so a complex is something that satisfies this. And so we can define the homology at this spot, which is nothing but kernel of this map modulo image of this map. So in general, in an abelian category, one has to use the universal property of kernel and co-kernel to make sense of, let's say, this is my complex. So ith homology of complex is if you're in category of modules, we know that this is a subset of this, but in general, one has to use the universal property of kernel and co-kernel to show that there is a natural map from here to here, and you can basically define quotient. But for simplicity, let us assume that we are working in module category, and this is how one can define homology. And as we saw in today's talk, or maybe this these complexes naturally arise in topology as well as in algebra. In algebra, we have free resolutions, whereas in, let's say, topology, you have singular chain complexes and things like that. So, and one of the aims is to study topological spaces up to homotopy, or study modules or complexes up to their cofibrant replacement, which came up in today's talk. So let me define what homotopy is. So you have two complexes, X and Y. And let us suppose that we have a chain map between these two. So what do I mean by chain map? So it's a map at every degree such that each such square commutes. So this is what a chain map is. Now suppose I have two such chain maps, F and G. Then we say that F is homotopic to G. If there are maps HI from xi to yi plus 1 like this for every I, such that this fi minus gi, the difference, is equal to this plus this. So yeah, I'll just call this as D and maybe this as so fi minus gi should be equal to hi followed by dou plus D followed by hi minus 1. And this relation is an equivalence relation. So we can talk about two chain maps being homotopic rather than saying that F is homotopic to G. Okay, so yeah, one observation is that if we consider only complexes and consider these to be the morphisms, then that forms a category which we will denote by complexes with objects in A. So this forms an abelian category because you have kernels, co-kernels degree wise. And we can also define what is called as homotopy category, in which the objects are the same as that of complex category. That is, objects here are complexes and morphisms are morphisms up to homotopy. That means if two morphisms are homotopic to each other, this definition, then we will consider them as same here. Yeah, maybe let me just write that. So objects of AA are same as objects of complexes, and form in this category Ka between x to y are form in complex category between x to y mod out by the homotopy relation. Yeah, so we call this as homotopy category. Okay. So in topology, we want to study spaces up to homotopy. In other words, what we want is that we don't want to distinguish between those two spaces. Considering this as a motivation, what we want is that suppose we have a chain map from here to here that that induces isomorphism on the homology groups, then we want it to be invertible. But in general, that doesn't happen. For example, if I have let's say a module is Z mod 2Z. And suppose if I consider this complex, just a trivial complex with Z mod 2Z, and let's say I have this multiplication by 2, and I have this onto map, generator going to generator. Then you can see that homology at this spot in this complex is precisely Z mod 2Z. For this complex, homology is 0 everywhere except at this spot, which is Z mod 2Z. So at both the places, we have that the homology is Z mod 2Z, yet the homology is 0. So, and we also have map F going from the top complex to bottom complex. But we don't really have any map in the backward direction. So what we would actually like to do is to resolve this issue, and we somehow want a map in the reverse direction. In other words, we want to invert this chain map. And as we saw in yesterday's talk, way to do that is localization. So what we will do is we will formally invert these types of these quasi-isomorphisms. So maybe I didn't define what a quasi-isomorphism is. So map F of chain complexes is it to be a quasi-isomorphism if the map that it induces on homology groups is an isomorphism. So we want to invert these quasi-isomorphisms. Yeah, so, and after inverting, what we get is called as the derived category. So let me first define what derived category is, and then we'll go to this localization process. The derived category is something in which these quasi-isomorphisms become isomorphisms. And this definition should remind you of localization that we saw yesterday. So this is definition / theorem. So whatever I don't prove here, you can find it in this book by Elfand and Manin, Homological Algebra. So what is derived category? You start with an abelian category A, then there is a category D of A and a functor Q from category of complexes to this category, such that the property that we wanted, that F is quasi-isomorphism in complexes, implies that when you apply this Q, when you go to the derived category, this is an isomorphism And second property is that universal property that if you have any functor from this complexes over A to any other category, let's say D, so for any F from complex category to any other category such that it sends quasi-isomorphism is an isomorphism for whenever you have a quasi-isomorphism F, and if quasi-isomorphisms are sent to isomorphisms by this functor F, what should happen? So there should exist a functor, unique functor G from D to this category D, such that this diagram commutes. So you have complexes to dA. This is the functor Q, and start with any D and the functor F taking quasi-isomorphisms to isomorphisms. There should exist G making this diagram commutative. So we have the same property that localization in rings satisfies. For example, you consider a category to be singleton R ring, and for every element you have a morphism which is just multiplication by that element. And suppose you fix a multiplicatively closed set S, then S inverse R precisely satisfies the property that whenever you have a ring map from R to any ring T such that it sends elements of S to a unit here, that is like saying that you are going to an isomorphism here because units induce isomorphism. It factors through this localization, so kind of similar. That suggests that we should define some type of localization to get to this derived category. Okay, so are there any questions so far? Okay, so yeah, I'll just maybe so you have a category C and you have a maybe a class of morphisms S, and we want to localize this category C at S. So the idea is that every element of S, every morphism in S should have an inverse. So this localization, which we will denote by maybe CS inverse, we want to form this category whose objects are same as objects of C, and we want to define what its morphisms are. So the morphisms that are already present in C, we want to preserve them, and we want to add the inverses of elements of S. So for every morphism in S, small s, we formally add a variable. Think of this as inverse of this morphism S. And so this is the construction. So for every S, we have a variable XS. Now we construct an oriented graph. Whose vertex set, let's say G, whose vertices are objects of C and whose edges are morphisms of C together with these x's. And we are saying oriented graph. So what are the directed edges? Whenever there is a map from X to Y, whenever there is a morphism in category C, what you do is in this graph, you know that corresponding to every object, you have a vertex. So you will have a directed edge going from the vertex corresponding to X to vertex corresponding to Y. And for x's, we are thinking of this x's as inverse of S. So naturally, you should have the edge pointing in the reverse direction. So if this is S from X to Y, then this xs is moving in the reverse direction. Yeah, so yeah, if we take the category to be small, then this is a set. But okay, right now I'm not assuming anything on my category. I have some category in which the objects and morphisms are allowed not to be sets. So are you concerned about this equality or what? Yes. So far there is no issue. I'm just having a graph with some edges. Yeah. Yeah, so we have this graph. Remember, we want to define this localization with n. So whose objects are objects of C, and okay, we are doing this to define what the morphisms are. So what are the morphisms? So a morphism in this CS inverse is an equivalence class of paths in G modulo this relation tilde. And what is, so this tilde will identify, first of all, suppose let's say you have a map from X to Y and Y to Z, then you, in this graph, you will have this path going from vertex corresponding to X to vertex corresponding to Y to vertex corresponding to Z. So you just compose this, and this is the, so this composition and this both are same in under this equivalence relation. And we took these x's as models for inverses. So that is what you want. So if you have S and x's from X to Y and from Y to X, you go back by x's, this composition should be identified with the identity morphism on X. And similarly, the other way, when you put x's here and S here, that composition should be identity on the appropriate object. So modulo this equivalence relation, we are considering morphisms in this category. And now whatever Navakumar said, this construction need not give us small category or locally small category in general. But if our category is nice enough, for example, bounded below complexes of modules over a ring which has model structure, then in the first talk today we saw that morphisms, a set of morphisms between any two objects can be described in a nice way. So that way it will give you a locally small category in nice cases. But this construction is in general. But yeah, what we want to do actually here is that we want to invert quasi-isomorphisms. So yeah, maybe let me get to that. But this is a general construction of localizing a category at a class of morphisms in it. So let's say in C, equivalence class. So equivalence class modulo this relation. So you have collection of paths. So it's like you have a set whose element, okay, maybe not a set, but you have a collection whose elements are paths, and you will identify two paths in an equivalence class if they are of this form, that S followed by XS. This is a path, right? So you want to identify this path with the identity, because that was the whole idea. You wanted to inverse this S. So no, what do you mean by that? Previous relations in the category?
C was a category and we had some relation.
Yeah, this. So these X, Y, Z are objects of C, and these morphisms are in category C. Yeah, maybe I. No, I'm saying that you identify this path with the composition. Yeah. You can just take the relation generated by the equivalence relation generated by this. Yeah, so in rings, there is one more thing that we don't generally localize at any arbitrary subset of R. We consider multiplicatively closed set. So here also there is that notion, what we call as localizing class of morphisms. But okay, maybe I'll not define that. But the point is that these quasi-isomorphisms, they form this localizing class. And if we take localization of this homotopy category or category of complexes at quasi-isomorphisms, then it gives us the derived category in which quasi-isomorphisms become isomorphisms. Okay, so let me go towards at least defining triangulated categories. So I'll start with this construction. Mapping cone. People in algebra might already know this, because I'm going to define this algebraically. It's not going to be same definition that we usually see in topology, because there should be some connection which I don't know. So, yeah. So so what is a mapping cone? So suppose I have two complexes, X and Y. And let's say we have a map of complexes between X and Y. Think of this X as that horizontal complex and Y as a complex below it, and you have vertical maps. That's what this is. Then we define its mapping cone to be a complex CF whose ith object is I minus first object of X. We are in an abelian category, yi. So this is going to be my complex CF. Whose ith object is this. Xi minus 1 directs some yi. And I should tell you what this map is. So let's call it DI. So we started with an f from x to y. So for every I, we have a map fi from xi to yi. Also, we are starting with two complexes x and y. So maybe let me just say that phi, that is phi I is the map, the differential in x, and psi I is ith differential in y. Then we define this di from ith component of the mapping cone CFI to I minus first component as follows. So di of an element here, and this is an element here. Maybe I should write it as I. This goes to so from xi minus 1 to xi minus 2, there is a natural way which we can go, that is using phi I minus 1, the map that is there in complex X. We put minus sign for the obvious reasons that we want this to be a complex. Then from xi minus 1, we can go to yi minus 1 through that map F, which is what shows up here. And from yi to yi minus 1, we have this psi I. So yeah, and this can be good as this matrix also, that minus phi I minus 1, 0, fi minus 1, and psi I, the same thing. Thinking of elements here as columns. Okay, so this is something that we are going to need in the definition of, or an example of triangulated category. So, okay, yeah, let me start with defining what a triangle is. So you have a category C, and let's say you have a functor T on C, that is from C to C. It is an automorphism. Then a triangle is just a diagram of this form. So x2, y2, z2, P of x. P of x is again an object of C. Okay, one reason for calling it a triangle is that it's like you have map from x to y, from y you are going to z, and from z you are coming back to x, but not really, it's tx. So this t is called as translation functor usually. And for example, for category of modules, if you start with complex, this translation is just shifting it by 1 unit to the left or to the right. So yeah, here you are going to tx. Okay, so yeah, let me now define what a triangulated category is. So you have a category C. You have a translation functor T on that, is an automorphism. And you are given a collection which we'll call as distinguished triangles. So this collection is a collection of triangles of this form. This T is what we are having here. To define triangles here, we'll use this T. So this is the data that is given to us. We have a category, additive category. We have this translation functor and some collection of triangles. This is what is given to us. Now, if this data satisfies a certain axioms, we'll call that as a triangulated category. And now I'll define what the axioms are. So first axiom is that this triangle should belong to this collection. I'll just say belongs to delta C. B is that any triangle which is isomorphic to a triangle in this collection has to belong to that collection. So what do I mean by isomorphic to? If you have two triangles, let's say x1, x2, x3 to t of x1 and y1, y2, y3 to t of y1, then the isomorphism is a natural one that you should have vertical maps and maps in reverse direction that give you isomorphisms. So first is that a part of the first axiom is that any such triangle should belong to this collection. Second is that if you take any triangle which is isomorphic to some triangle here, then the triangle that you started with should be here. And C is that you start with any morphism from x to y, you should be able to complete this for a morphism from x to y, there is a triangle like this. So this is the first axiom. Second axiom is that suppose you have a triangle with maps U, V, W. So if this is triangle in that collection, then it implies that Y to Z to this should belong to that collection. P is an automorphism. So for a morphism U in category C, we can talk about P of U. Yeah, so yeah, there's this minus sign. For it to be a triangle, I mean, in the examples we'll see. Yeah, yeah, there's this minus sign. Oh, you mean if this is a triangle, then this is a triangle? I'm just thinking if it follows from this, if I shift it. This T is an automorphism, so it might. It's like if we shift this one like two more times, then we'll have something like T of X to T of Y to T of Z to maybe T of X, and I'm in an additive category, so. Yeah, I'll check that and maybe let you know. And third axiom is that okay, so just to recall, we're defining triangulated category. The data given to us is category, an automorphism, functor, and a collection of triangles. This is a triangulated category if it satisfies these axioms. So what is third axiom? It is that okay, fine. So if we are given these maps, then there should exist a map here such that this diagram commutes. This is third axiom. No, it need not be. Or maybe it will turn out to be unique, I think, yeah. Yeah. Again, there is one more axiom, maybe not say more about it. It is called octahedron axiom. Basically, what it says is that you have an octahedron. Okay, assume that this is an octahedron. So you have some data given here. So this is an object in your category. So some data is given for this upper cap, and what this octahedron axiom says is that there should exist this Y, and you can construct these maps so that something nice happens. I can write down the properties, but it won't make any difference. So that, yeah. Instead, I'll just give one example maybe of triangulated category. So let's say is category of modules over some ring R, and you want to give this triangulated category structure. That means we should have two things. First of all, translation functor T and the class of triangles. So translation functor T is something that shifts complex by one unit. What I mean by that is, suppose you take a complex in A, then T of X is a complex whose ith element is I minus first element of complex X. So we are shifting this complex by one unit. If this is the ith position, then you are shifting it towards left by one unit. So this is the translation functor, and the distinguished triangles in this category are precisely those that have the form that x to y. With this third object, you take it to be cone of this map to T of X, which is okay. So these are the distinguished triangles. So notice that this CF is, its ith component is xi minus 1 direct some yi. So the map from this yi to here is the natural inclusion, and from here to here it is projection on the first coordinate, because ith component of Tx is xi minus 1, which is this. So yeah, these are the distinguished triangles, and with this data, this A forms a triangulated category. Yeah, maybe I can give a sketch. So with the above A translation functor and this is a triangulated category. And so to prove that it is a triangulated category, we have to check that all these axioms are satisfied by the data that we have. And okay, so in TR1, this one is obvious because for every map from X to Y, we have the cone, we have that construction. So we can form this Z, take it to be the cone, which we know is a distinguished triangle by definition. So this is trivially satisfied. This is also okay. For A, what we have to show is that x to 0 to tx, this is a distinguished triangle. That means I must show that x to 0 to tx, this is isomorphic to something to cone of that map to t of the first thing. So yeah. I see. Yes. Right. No. This okay. A is category of modules, and I'm considering complexes of modules. Okay. You see. Yeah. Right. This is complexes. Yeah, so here the category is complexes and yeah. Yeah, that's precisely what this is. So okay, yeah. I see. Yeah, so I have to consider the homotopy category here. Yeah, you're right. So let us consider the category to be the homotopy category, and in which the objects are complexes. So I can talk about this translation functor. And yeah, to show that this is a distinguished triangle, I want to show that, what I will show is that x to x, this is isomorphic to this distinguished triangle in the homotopy category. So what I have to show is that I have maps both ways such that this composition with the reverse map is homotopic to identity over here, and same way if I start from here, go above and come back, then the map of complexes that I get at every spot is homotopic to identity at that particular spot, which is trivial for this part because I have just the identity map. Here also I have the identity map. The only thing is here I have to check that this composition is homotopic to identity here, which is also trivial because this map is the zero map. This composition is zero. So the only thing that you have to verify is that if you start with the cone of this identity, this complex, if you go up, that's just the trivial map 0. When you come back, that map is 0. So this 0 map is homotopic to the identity map on the cone. That's what we have to show. And that means I have to give you the homology map, sorry, homotopy. And yeah, there is a natural choice to this homotopy. So we have this cone. And I want to show that the identity map is this is homotopic to the 0 map. It is same thing as saying that the second map is 0. So I just need to produce these maps such that identity is equal to this composed with this plus this composed with this. And for that, there is natural choice of HI, which is HI minus 1 of AI minus 1 comma BI is equal to this is identity. Yeah, sorry. Yeah, so probably here I have to yeah, so this is the map. AI minus 1 comma BI goes to BI comma 0. And this gives you the homotopy. So that verifies this action. Yeah, I can give an argument for this. This map H is trivial in our case because we know that this is cone on X. So, and no, maybe I have to do some work for this. But the point is that this Z in our case is going to be, the ith component is going to be Xi minus 1 direct sum Yi. And here it is going to be X prime I minus 1 direct sum Y prime I. And I have the component wise map, which I can use to construct this H. So this H is going to be ith component here is going to be Xi minus 1 direct sum Yi. And below it is X prime I minus 1 direct sum Y prime I. And the map H is just this, Fi minus 1 with Gi. So that would verify this. And yeah, let me just write this down. So for TR2, what we want to show is that if I have X2, Y2, if this is distinguished, okay, then we want to show that we want to show this is distinguished, and in order to show this, we want to show that it is isomorphic to a distinguished triangle. That means a triangle of the form so what we'll show is that this is cone of this map to these two are isomorphic. And for that, I need to give you maps. These two maps are trivial, the identity maps, also this one. So I really need to give you a map from here to here. So as that it gives you an isomorphism in the homotopy category. So notice that this C of V is, its ith component is yi minus 1 direct sum with zi. So it is like it is T of y, but we are starting with this distinguished triangle. That means this Z is cone of this map. That means Z is T of x direct sum with y. So this is same as this is my CV, and I need to give you a map from Tx to CV. And so at ith level, the map is given by, so this is an element of xi minus 1, the ith component here. And this is the map. So it's like all homological algebra proofs, one has to verify all this. This is an element here, this ai minus 1 is here and 0 here. And this map theta along with identity maps here shows that these two are isomorphic, and that way we can verify this action. So yeah, this, we have to check this also. So yeah, this will prove that the homotopy category of an abelian category is triangulated. And one can also show that the derived category is also triangulated. Okay, maybe I'll stop here.
So are there any questions?
Yeah, so I'm formally introducing inverses here. Did I erase that? Yeah. Yeah, so for every element of S, I'm formally adding an inverse morphism. And I'm demanding these properties. So in this new category, CS inverse, I want this to be satisfied, that this XS should be an inverse of S, because I want this composition to be identity.
Are there other questions?
But you will introduce some T, right? From that I couldn't. Yeah. On this, right? Yeah. Yes. But applying t twice, will that give us something? I mean, so that we'll get something of the form. Right, right. That's what I was trying. Yeah, but now there will be some signs and you have to do it once more and then check maybe what happens. Yeah, but that's not identity. So you are saying that I need to. Okay, I think we'll discuss this.
Yes, I guess, yeah, you can, like look up some reference and maybe discuss it. Yeah, over tea or dinner. Are there other questions or comments? All right, so if not, let's thank the speaker.